Learning objectives.
At the end of this topic, you will be able to understand the concept of tangent to a circle, describe number of tangents that can be drawn to a circle, evaluate problems based on tangents to a circle. Let's begin this chapter with a recap of what we have learned about circles in the previous chapters. We have learned a circle is a collection of all points in a plane which are at a constant distance, radius, from a fixed point, center. We have also studied various terms related to a circle like chord, segment, sector, arc, etc. Let us now examine the different situations that can arise when a circle and a line are given in a plane. In the figure 1, the line PQ and the circle have no common point. In this case, PQ is called a non-intersecting line with respect to the circle. In the figure 2, there are two common points A and B that the line PQ and the circle have. In this case, we call the line PQ a secant of the circle. In figure 3, there is only one point A which is common to the line PQ and the circle. In this case, the line is called a tangent to the circle. Tangents to the circle. In the previous section, you have seen that a tangent to a circle is a line that intersects the circle at only one point. To understand the existence of the tangent to a circle at a point, let's perform the two activities. Take a circular wire and attach a straight wire AB at a point P of the circular wire so that it can rotate about the point P in a plane. Put the system on a table and gently rotate the wire AB about the point P to get different positions of the straight wire. So, we can observe there is only one tangent at a point of the circle. The tangent to a circle is a special case of the secant when the two endpoints of its corresponding chord coincide. In various positions, the wire intersects the circular wire at P and at another point Q1 or Q2 or Q3, etc. In one position, it will intersect the circle at the point P only. This shows that a tangent exists at the point P of the circle. On rotating further, all other positions of AB, it will intersect the circle at P and at another point, say R1 or R2 or R3, etc. So, we can observe there is only one tangent at a point of the circle. As the position AB moves towards the position A-B', the common point, say Q1 of the line AB, and the circle gradually comes nearer and nearer to the common point P. Ultimately, it coincides with the point P in the position A', B' of A', B'. Let's go to another activity and list the findings. Draw a circle and a secant PQ of the circle. Draw various lines parallel to the secant on both sides of it. Let's list the findings of this activity. The length of the chord cut by the lines will gradually decrease. That is, the 2 points of intersection of the line and the circle are coming closer and closer. In one case, it becomes 0 on one side of the secant, and in another case, it becomes 0 on the other side of the secant. The tangents to the circle parallel to the given secant. There cannot be more than two tangents parallel to a given secant. Let's summarize the findings of activity 1 and 2. A tangent is the secant when both of the endpoints of the corresponding chord coincide. The common point of the tangent and the circle is called the point of contact. The tangent is set to touch the circle at the common point. We shall now prove some property of the tangent with the help of a theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. Proof. We are given a circle with center O and a tangent xy to the circle at a point P. We need to prove that OP is perpendicular to xy. Take a point Q on xy other than P and join OQ. The point Q must lie outside the circle. Note: if Q lies inside the circle, xy will become a secant and not a tangent to the circle. Therefore, OQ is longer than the radius OP of the circle. That is, OQ greater than OP. Since this happens for every point on the line XY, except the point P, OP is the shortest of all the distances of the point O to the points of XY. So, OP is perpendicular to XY. By the theorem above, we can also conclude that at any point on a circle, there can be one and only one tangent. The line containing the radius through the point of contact is also sometimes called the normal to the circle at the point. To get an idea of the number of tangents from a point on a circle, let us perform another activity. Draw a circle and locate point P in 3 positions and draw tangents. Case 1. Point P inside the circle. Case 2. Point P on the circle. Case 3. Point P outside the circle. Let's summarize the results from 3 cases of the above activity. Case 1. There is no tangent to a circle passing through a point lying inside the circle. Case 2. There is one and only one tangent to a circle passing through a point lying on the circle. Case 3. There are exactly 2 tangents to a circle through a point lying outside the circle. From case 3, we can find that the lengths PT1 and PT2 are equal. We shall now frame a theorem and prove it. Theorem 2. The lengths of tangents drawn from an external point to a circle are equal. Proof. We are given a circle with center O, a point P lying outside the circle, and 2 tangents PQ, PR on the circle from P. We are required to prove PQ is equal to PR. For this, we join OP, OQ, and OR. Then, angle OQP and angle ORP are right angles because these are angles between the radii and the tangents. And according to theorem 10.1, they are right angles. Now, in right angles, OQP and ORP, OQ is equal to OR. Radii of the same circle. OP is equal to OP, common. Therefore, triangle OQP is equal to triangle ORP, RHS. This gives PQ is equal to PR, CPCT. Let's work some examples based on the theorem. Prove that in 2 concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. Let's move to another example. Prove that the parallelogram circumscribing a circle is rhombus. Given ABCD is a parallelogram circumscribing a circle. Let's move to another example. In the figure, XP and XQ are tangents from X to the circle with center O. R is a point on the circle. Prove that XA plus AR is equal to XB plus BR. Summary. Let's summarize the topic. A circle is a collection of all points in a plane which are at a constant distance, radius, from a fixed point, center. The tangent to a circle is perpendicular to the radius through the point of contact. The lengths of the two tangents from an external point to a circle are equal.